Hi there, and welcome back to Chapter 2.6 from Stevens' Matrices, Vectors, and 3D Math. This is actually the second video from this chapter. So if you haven't watched the first, you should go back and watch the first video because we're going to be talking about planes, and I will assume that you have seen the first video. All right, so let us get into the we're going to do a little bit of review, but first let me put this in full screen mode. So the quick review here is that in order to define a plane, right, what I need is a normal vector and a point. And if I can get that normal vector and a point, then I dot product them essentially and collect all of the terms. For example, if I have this normal vector and this point, right, then I have to take 4 times x minus 1 plus 5 times y minus negative 2 plus negative 6 times z minus 3, set that equal to 0, distribute all of your constants, collect all of your constants into one value, and what you're left with at the end of that process is the equation for a plane in general form. It looks a lot like the equation for a line in 2D, except it has an extra term for the z component. And then we did finding the plane through 3 points, finding a plane perpendicular to a given line, how to sketch a plane. It makes it a little easier to picture these things if you can sketch a few. That's in the homework. How we get the angle between two planes. So if two planes intersect, there's an angle. There's actually two angles. There's the big angle and then a little one, right? They'll either the little one, the max will be 90 degrees. All right, so basically the way you get the angle of intersection of the two planes is just get the angle of intersection between the two normal vectors, right? But when you look at the angle between the two normal vectors, this absolute value sign is not there. That's because you can have an angle that's bigger than 90, less than 90. But in this case, the absolute values ensure that I will get this smaller of the two angles, right? So these absolute values make sure I get that one that's less than or equal to 90 degrees. And in fact, this will come out to be 0 if it equals 90 degrees. So less than 90 degrees unless you get a 0 there. And then to actually get the angle, you have to use the arc cosine function. So as we're about to get into the new stuff, it's worth pointing out when you look at this intersection between these two planes, what you get is a line, right? Usually, provided they actually do intersect, you get a line of intersection. So where we're going to start here is with the next page, which is on finding the equation for that line of intersection. Okay, so here we are, 2.6. The line of intersection of two planes. So this starts the new material. And there's actually a couple of ways to do this. I'm going to show you both ways. Both of them are a little tedious, but neither one is particularly easier than the other. But perhaps method 1 is preferable because to do method 2, you really have to go through a big chunk of method 1 anyway. So we'll do method 1 first, and what that entails is just finding the general solution to a system of linear equations. Right? And what I mean by that is if I have one plane and another plane, and I want to see where they intersect, well, I have to solve both equations for x, y, and z. There's the first equation, there's the second equation. Right? So now, what I have here is two equations, 3 unknowns. I want to get this into matrix form or augmented matrix form. So the first thing I'm going to do is I'm going to take my constants and get them over to the right hand side. So I'll take 10 and add it to both sides. I'll take negative 3, add it to both sides. That'll get my constants over there. It'll look like this. And then I'm going to put this in a matrix form. So I have a 1 in front of my x, I have a 0 in front of my y, and a 3 in front of my z. So I have 1 times x plus 0 times y plus 3 times z. That's the first equation, equals 10. That's actually the first equation. And then the second equation here is 2x plus 1y plus 5z equals negative 3, or 2x plus 1y plus 5z equals negative 3. So once I have it in matrix form, I put that in augmented matrix form down here and go through the row reduction process of Gaussian elimination. And again, it's tough to do this with a machine. You can't necessarily be sure what the answer is producing whenever you have infinitely many solutions, which we're going to have in this case. So the first thing I'm going to do this by hand. I'm going to take this first row, multiply it by negative 2, and add it to the second row. I chose negative 2 so that that 2 becomes a 0. Nothing happens to my 1 there. And then this negative 2 times 3 is negative 6 plus 5. That becomes a negative 1, right? So I get this new second equation. Oh wait, I do have to take that by negative 2 and add it to that. So that's a negative 20 minus 3 is negative 23. Then actually, that's the last step. My first step is my last step in this case. I can't go any further. And so if you take a look at this last equation, that basically says y minus z equals negative 23. So I have two equations, three unknowns. I'm going to have infinitely many solutions. So I'm just going to start with a free variable. So I'll let z be my free parameter t. So if I let z equal t, then this equation says y minus z equals negative 23. But that's just y equals negative 23 plus z. But z is just t. So I let z equal t. That gives me y is negative 23 plus t. And then if I just go back to my first equation, right, which is right here, that is just x plus 3z equals 10. Z is just t, so that's x equals 10 minus 3z, or 3t, because z equals t. And if you look at that, that is the equation for a line. That is the line of intersection. You have infinitely many solutions. It's not just any old infinitely many. It's infinitely many that lie in this particular line. Right? So that's one way. The other way is to actually just find any solution. Find some point of intersection between these two planes. And you can do it through the full Gaussian elimination process. You might be able to set one of these variables to 0. But you just need one solution. You don't need the infinitely many. And so an easy one to find, now that we've already done method 1, is to let t equal 0 in these equations. So one solution to this system of equations here is just 10, negative 23, and 0. Just by letting t equal 0. So now I have one point of intersection. I have two planes. I have one point of intersection. And so what I'm going to do is I want to find the direction vector for that line. So suppose I have that plane and then some other plane, right? Their intersection, basically they each have a normal. Suppose this is the normal here and this is the normal here. Then if you get the cross product of those two normals, that will give you the direction of the line of intersection. Right? So the first normal vector, and notice I have them here. I have n1 and n2. So those are the normal vectors for the two planes. And just as a refresher where those came from, they're actually just looking right at you. When you look at the equation for a plane, you have the normal vectors sort of staring at you. It's going to be 1. Oh, sorry, there's a 0 in front of the y. You don't really see it. So it's going to be 1, 0, 3. And then the second normal vector is going to be 2, 1, 5. 2, 1, 5. Like that. So that's where those normal vectors came from. Right there and right there. And so if I want the cross product, I hope this little graphic isn't doing more harm than good, but I'm just basically taking the normal of each plane, getting the cross product, and that gives me the direction vector for the line of intersection. So I take N1 cross N2, and again, it's somewhat tedious, but if you do it with the determinant of this 3 by 3 matrix, it is not so bad. Just take I times the determinant of this matrix minus J times the determinant of this matrix plus K times the determinant of this matrix. And if you do that, you get negative 3I plus J plus K, or negative 3, 1, 1. So that is my direction vector for the line. Right? So now that I have a point here and a direction vector here, I can do my line very easily. It's just going to be 10, all right, minus 3t for x, and then y is going to be negative 23 plus t, and z is going to be 0 plus t. So there is the equations, the parametric equations. There are the parametric equations for my line of intersection. And notice both ways produced the same line. And they might not always produce identical parametric equations. Like, you might not look at them and immediately identify them as being the same, but they will trace out the exact same line, and they will have parallel direction vectors. All right, so the next topic in this chapter is going to be finding the distance between a point and a plane, and the formula is given here, but it's certainly worth recognizing what all the terms are in that formula. So the distance I'm looking for, suppose I have this plane here and some point not on the plane, and I'll call that Q. So I'm looking for this distance from Q to my plane. And when I say the distance, I'm talking about the shortest distance, that distance produced when you go directly towards the plane, producing a right angle at the intersection. And so getting this in theory is pretty easy, right? If I take my normal vector, and it might be going that way, and you might actually be getting that one, but it doesn't much make a difference. We'll use this one pointing up for the graphical representation. If I just take the vector PQ, where this P is any point on my plane. So I get the vector PQ, and then I project it down onto my normal. That gives me this vector, and if I just take the size of that vector, that will give me the distance from the point to the plane. Give me this right here. So this formula here for that distance makes sense geometrically when we look at it. But when you go through some simplification down here, specifically if you put in the formula for the projection of PQ onto n, it's PQ dot n over the size of n squared times n. And we're taking the magnitude of that vector. So this is just a scalar. It can be pulled out of the magnitude. Just the absolute value. That's just a number. PQ dot n is a number, so that comes out. And then I have the size of n over the size of n squared. One of them cancels, and that is my short form for the magnitude of this projection. So this form, the magnitude of the projection, makes sense geometrically. This form is just what it looks like when you simplify. Okay. The distance between a point and a plane. There's where I want to be. Here's an example. Suppose I have this point Q, this plane here, and I need a point on the plane. So here's the trick. This point on a plane, people often get this wrong because they think it's more complicated than it is. What I have is one equation and 3 unknowns. I want one point on that plane. I get to sort of assign a value to 3 of those unknowns. So what I'll do here is I'll say, all right, I'm going to let x equal 0, and I'm going to let y equal 0. And if you look at what's left, I get z, because that's gone, right? That's gone. I have z minus 6 equals 0, which gives me z equals 6. So I have 0, 0, 6. So that's my point on the plane. And I could have done anything. I could have let x equal 1, y equal 1, and solve for z. Right? But there's so much freedom that people sometimes get it wrong. But it's really an easy problem. There's one equation, three unknowns. Okay, so there's my P. Q is given to me in the problem. And then I just need my normal vector. But that comes from here. There's a 4, -2, and a 1. So my normal vector is actually right there. Right? Okay, so I just take PQ dot N. And that's going to give me 0 plus 0 plus 6. All right. Oh, wait. You know what I have to do? I just took P dot N. I can't do that. P is a point. All right. I have to find PQ. So the first thing I have to do is subtract Q from P. So PQ is actually 1 minus 0, 1 minus 0, 2 minus 0, 3 minus 6, which is -3. So there, now I have PQ, and I dot that with N. All right, so here they are, the two of them right next to each other. So when I take PQ dot N, I have 4, right, minus 4, minus 3, which is -3, so that's PQ dot N. But I need to take the absolute value of that, so I get 3 up here. And then the size of N is just the square root of 16 plus 4 plus 1, square root of 21. So this distance here is 3 over the square root of 21. You can rationalize the denominator if you want. It's not important because you'd probably be doing this in a machine, or you can plug that into your calculator. What's important, though, is this is the distance. I've got a lot of red here. This is just merely the distance from this point, Q, to this plane. All right, so there's the equation for the plane right here. There's some point, and the distance that I just calculated was this shortest distance from the point Q to the plane. Right? Not especially difficult, and not even particularly difficult to recognize geometrically. And then a little simplification gives you your formula here. Alright, so I'm going to expand this into a similar problem where I want to get the distance, right, between two parallel planes. Right? And so for a picture on that, suppose I have this plane here and then a parallel plane right below it. Right? And I'll call this bottom one, I'll call that plane 1, and this one plane 2. So if I want the distance between these two, basically I want from here down to here, right? Right angles at both of these intersection. That'll give me my distance. So the way I do that is I pick any point here on the second plane, and I call that Q. And now I'm just going to find the distance from this plane down here up to Q, right? Because that'll be the shortest distance, right? So that's the trick. I get a point on the second plane and find the distance from that point to the first plane. All right, so let's see. I need a point on the second plane. That's where I'm going to get Q, right? Q equals. So the way I'm going to do this, and again, this is that problem where I have 3 unknowns and 1 equation. I can be sort of creative. If I let x equal 0 and z equals 0, then what I have is -y plus 5 equals 0, or y equals 5. So my Q point, my point on plane 2, is just going to be 0, 5, 0. Right? That's how I get that point right there. But now I'm going to need PQ and dot it with N. So that P, if you recall, is a point on this plane, the first plane. So I have to play the same game over here and get a point on this plane. If I let x equal 0, that's gone. If I let z equal 0 again, that's gone. And I just get -y minus 6 equals 0, or y equals -6. So that's my 0, 0, -6. Sorry, but the 0 is for x, 0 for z, y is -6. That gives me this point. So I have my 2 points. The point on plane 2, the point on plane 1, and so now I'm just going to take the distance from the first plane to the point Q. Right? So if I go with this formula, that's going to be normal to the first plane, n, right? So that normal vector to the first plane, remember those normal vectors are staring right at you. That n is going to be 3, -1, 2. Right? Which is right here. Okay, so now I have P, Q, and N. I do need to get PQ first, and that's just found by taking Q here and subtracting P, so it's 0 minus 0, 5 minus -6, which is 5 plus 6, which is 11, and then 0 minus 0 again. So I have 0, 11, 0 is PQ. Good to have. And then where is N? I'll try to erase some of this other stuff. There's N. So this numerator is just PQ dotted with N. So that's going to be 0 minus 11 plus 0. So it's -11, but you're taking the absolute value over the size of N, which is just going to be 9 plus 1 plus 4, square root of 14. So this distance, 11 over the square root of 14, is the distance between two parallel planes, right? And that's found not through a separate formula, but by just taking a point Q on my second plane and getting the distance from that point Q to my first plane. And you could have switched roles and found a point here and found the distance from that to this plane. Either one works. Alright, so now we're going to switch over to a little bit of MATLAB, and the best thing to do is just go to the program repository and grab these files and open them up and play around with them. The first file is a function file. It's called plot plane function. You should open that up, and you should also grab the program file, plottingplanes.m. And so this program just calls this function a bunch of times to create 3 planes. And I'll give you a little rundown on what this is. So this is the function. I want to plot the plane, right? And basically I'm going to define it the same way I do in this chapter, whereas I have a normal vector and some point that it goes through. But then this x, y, and z bounds, if I'm going to plot a plane, I have x, y, and z. All right, I'm going to put my bounds in so that I only go, it gives me this finite range of values to plot it over. All right, because when we write all this in the book, it's sort of this infinite object, but if I'm going to graph it, it certainly can't be an infinite object. So this x, y, z bounds is basically the bounds on x, the bounds on y, the bounds on z, put into a vector. And then I go through, that's my normal. There's my actual point, and that's that D, which combines, you go all the way back here, that general equation for a plane. Let me see if I can't get to it without making you too dizzy. It is this, without going back to the formula, it's that term there, right? So that's going to give me the constant term in the equation. Again, avert your eyes if you need to avoid getting dizzy. So that's what this D value is right here. Okay, and then here I'm just defining my bounds for graphing. And what that does is I create a vector of x values, vector of y values, vector of z values. And now I want to plot it, but I need to get the plot here in terms of a function, right? So if c is not 0, I can define z in terms of x and y, right? And there is, because I'm going to be dividing by c, that's the coefficient of z. If that's provided that's not 0, I'm good to go. And this is that functional form of a plane, z equals f of x, y, right? And before I do that, I actually do have to mesh out this thing. When we get into 3D plotting, we'll do more of this. We're meshing out the x and y because those are just, an x vector. This is just a one-dimensional vector. That's another one-dimensional vector. This turns it into a two-dimensional grid. And then this z function will, for every point on this x and y grid, create a z value. If c happens to equal 0 and b doesn't, I do y in terms of x and z. If c and b are 0, then I need to get x in terms of y and z. And if all three of these are 0, if that's 0, that's 0, and that's 0, then basically my normal vector had length 0, and it would have booted me out. So to use it, all I need is a normal vector and a point, right? And so here I'm doing 3 planes, 3 different normal vectors, 3 different points. I'm going to let my x and y bounds and z bounds all go from -10 to 10, and this plots them, right? And the plot plane function is called using the surf. That's creating surface, right? And basically you have a bunch of x, y, and z values. It'll create a surface for you. But if you're going to use this surf, it's imperative that you use this mesh grid command. So this creates the 3 planes. As you can see, the 3 planes look to intersect at a single point right there. All right. And here's a little aside. This is the plot plane and normal. This will plot the plane and a normal vector. And basically all I'm doing is if I have this normal vector and this point, if I'd like to plot the plane and the normal vector, this will plot my plane. And then the normal vector, I'm going to plot it in a unit length. Just in case my normal vector up here is huge, I don't want to plot it and throw everything out of scale. So I make it length 1, and then what I do is I start at my point P that I have from up here, and then I add my unit normal, and that'll give me a second point. And then in order to get my normal vector, I just take my initial point, add that unit vector, gives me my second point, and then I'm going to do an arrow from P to P2. And that produces this. You can't tell it's an arrow here because of the camera view. But if you were to rotate that, you'd see that you'd actually have an arrow. All right, so it's a decent little function. The plot plane function is what I'm really demonstrating here. It's a decent little function for plotting planes without having to go through and use the surf function over and over. But the trick is this x, y, and z bounds. You might have to play around with those because sometimes you'll plot and maybe your plane will be way over here, and if your x, y, and z bounds are too small, you might not see it. All right, so make sure you play around with this to open it up real wide and then sort of narrow in on the plane. And then the this worksheet problem, basically what I want you to do is plot all 3 of those planes and see if you can see why there are no solutions. Right? Because they're not parallel. If you're looking for the intersection of 3 planes, if they're parallel like that, you'll get nothing. But that's not the case here, right? Because the normal vectors are not parallel. The normal vector, the first one is, let's see, 0, 1, -4. The normal vector for the second one is 2, -3, 2. And the normal vector for the third plane is 5, -8, 7. So they're not parallel. So it doesn't look like this, but yet they don't intersect at a single point. So the game is to plot all 3 of these planes, rotate it around, zoom in, change the x, y, and z bounds until you can make sense of why those things don't intersect. So that wraps up chapter 2.6. I will see you in chapter 2.7. Thank you so much. We're done. Bye.